Alright, so question number 9 reads, how do you use implicit differentiation to find dy over dx given y squared equals 2 plus xy? Okay, so I first have to explain what implicit differentiation is and how it's different from regular differentiation. Okay, so the regular form of differentiation that we usually do is called explicit differentiation. And how explicit differentiation works, let me just finish writing it out first, is that it takes a function that is explicitly stated. So that means that this function is in terms of one variable only. Okay? So here in our given example here, this is not what we call an explicit function because this function y squared is in terms of x and y. Okay? Now we could make it explicit by isolating for y, but we're going to use implicit differentiation instead. So explicit differentiation, the product of explicit differentiation is a function of only in terms of x. Okay, so explicit differentiation produces a function in terms of one variable. So we're talking about single variable calculus for now. When you get up to multivariable calculus, there might be multiple variables. Okay, so how is that different from implicit differentiation? So implicit differentiation differentiates implicit functions. So functions that it's not very clear how many variables are involved here. So this is an implicit function. So you see that y squared is a function of x and y, right? So it's a function of the independent variable of x and also a function of itself, right? So implicit differentiation produces a derivative in terms of multiple variables. In this case, is 2. Okay, so I'll make this very clear. This is only for single variable calculus. So for single variable, okay. Derivatives. Okay, cool. So how do we calculate using implicit differentiation? So we're still going to calculate in terms, we're going to still differentiate in terms of dy over dx. When we approach anything with a y squared, we'll just put y prime or dy over dx instead. Okay, so I'll just go through the example and it'll be clearer to you guys. Okay, so let's calculate dy over dx. Okay, of y squared. Of y squared equals 2 plus xy. Okay, so if we were to do that, we would calculate both left and right hand side, right? So equals dy of dx of 2 plus xy. Okay, so let's do the left hand side first, right? So the derivative of y squared, there's a power rule here, right? Or this is a chain rule here, right? So we have the derivative of y squared and then the derivative of y. But since we don't know what the derivative of y is, we're just going to say dy over dx. Okay, so the derivative of y squared is going to be 2y times dy over dx. Okay, so we don't know what the derivative of y is, so we're just going to write dy over dx. Here we have two different functions here. So we have dy over dx of 2, which is just 0, and dy over dx of x and y, x times y. Okay, so we're using the product rule here now, which states that the product rule states the derivative of fx of gx is equal to f prime of x times g of x plus g prime of x times f of x. Okay, So that's the product rule of differentiation. So we're going to use that here. So the derivative of x is 1. So we're going to have 1 times y plus the derivative of g prime of x, or y, which is dy over dx times x. Okay, cool. Sorry about that. My dog's just barking. I'm just going to tell her to be quiet. Alright, sorry about that. My dog was barking. Okay, so where were we? Oh, so we were calculating the implicit differentiation of this. So we just finished, actually. So now, at this point of the question, we want to isolate for dy dx. Okay, so we want to move everything with dy dx to the left-hand side. So we're going to move dy dx of times x to the left-hand side, and we get this. 2y of dy dx minus x times dy dx. Okay, and that equals to y. So now we can factor out dy dx on the left-hand side. And we get 2 minus x, or 2y minus x equals y. And if we move, divide both sides by 2y minus x, we get equals y divided by 2y minus x. Okay, so we can see here through implicit differentiation that our derivative is a function of both y and x. Okay, so whenever we're doing implicit differentiation, this is the derivative that you will get. You will never get a function that is a function of only x, because we implicitly derived. So what's the use or value of implicit differentiation, you may say? Well, sometimes you have a function that is very hard to isolate and make an explicit function. A function that explicitly states that it's related to one single variable. In this case, we could have actually explicitly derived by isolating for y and making it a function of only x, but that would be very complicated to derive in itself. So this is where implicit differentiation comes in, because we can bypass the complicated isolation and the complicated explicit differentiation, and we can exchange it for a much more simpler implicit differentiation where we still find the derivative, but it's just as a function of y and x. Okay, so other than that, this is the correct solution, and we can move on. All right, let's move on to the last question of the day.